Okay.
All right. Good afternoon, everyone. So today's seminar speaker is Sara Hamilton. Sara received her bachelor's in chemical engineering at Imperial College London. And it was about 2.5 years ago, my former postdoc, who's a faculty member there, got super excited and then told me that there's a really great student coming towards you, so you should talk to her. And we had really wonderful discussion, I think over Zoom, I think. And ever since then, she arrived and been leading a lot of our research activities in the energy storage area. So I'm really excited to introduce Sara. We're gonna talk about our electrolyte work. Here are you. Here is Sara.
Okay, thank you, Professor Park, for the introduction, and good afternoon, everyone. So today I'm going to be giving a talk on functionally structured electrolytes for energy storage. And I've tried to structure this talk in a way that even if your research area is very different from energy storage, hopefully you'll learn something about my research, but also about the wider field in general. So first, I'm going to be giving an introduction to the PERC group and how my research fits into our goals. And then I'm going to motivate the area of energy storage and specifically this area of functionally structured electrolytes. And I'll explain what that means. And then I'm going to be giving some examples of what these type of electrolytes are, including the materials that I work on. So please feel free to post any questions on the chat as I go along. I'll probably get to them at the end of the talk with the discussion though. So let's get started. So this is a PERC group as of fall last year, and our main research goals are to develop new technologies for environmentally sustainable energy. We have quite a few of ongoing research projects, which are summarized here. What I work on specifically is energy storage, so I'll be focusing on this specifically today. So just to motivate energy storage, and I think many of us are aware of this, but renewable energy is available at increasingly lower costs. And in the past few years, we've seen kind of headlines like this, and we see some places like California actually paying customers to take the excess renewable power of the grid. However, if we look at global energy supply here, we see that renewables actually only account for just about 10% of global energy supply. And a grand challenge here is intermittency. So there's kind of this need to develop new energy storage technologies so that we can actually harness the renewable power. So in my research project, what I'm trying to do is develop these new kind of electrolyte materials that we call NOMs, and I'll talk about what that means later in the talk, that can be used to harness renewable CO2-free electricity in kind of two different pathways that involve electrochemical conversion. So the first pathway is to convert CO2 to dense energy carriers, such as chemicals and fuels, electrochemically. And the second pathway that I look at to actually store this energy is to use some sort of large-scale electrochemical energy storage device, such as a flow battery. So I'm specifically interested in understanding what the electrochemical properties and the structural properties of these NOMS-based electrolytes are, and to optimize these for these two different pathways I talked about. But today, just in the interest of time, I'm only going to be talking about the green box here, which is related to storage in a flow battery system. So in order to get everyone kind of on the same page here, this is a very brief description of what a flow battery is, but hopefully I'll get us all to understand this. So a flow battery is a type of electrochemical energy storage device where the energy is stored in the form of redox active species, which are dissolved in these electrolyte tanks. So we have two of these tanks. One is the negative one, which we call the anolyte with one of the redox active species, and the other is the positive electrolyte tank, or the catholyte, where the second species is stored. And both of these are separated by a semi-permeable membrane, so that's shown in red here. And the role of this membrane is to prevent the crossover of these two redox active species from one compartment to the other, which would lead to capacity fade in the battery, but at the same time be able to maintain the flow of supporting electrolyte ions. So let's look at what happens in this battery during discharge, which is being shown here. So we see that the species in the analyte that will have a lower reduction potential will be preferentially oxidized, so loses electrons which flow to the other compartment, where the second species will gain those electrons and get reduced. And during charging, exactly the opposite process is going to take place. So electron flow will be reversed, and this gives us an overall cell voltage of V cell given by the difference in the redox potentials of those two species. So here in the top right, I'm showing some of the typical redox potentials of species that have been looked at in flow batteries. And in the bottom, in that red box here, I'm showing that flow batteries have discharge times of several hours and can store energy up to megawatt-hour capacity. So that makes them interesting for large-scale energy storage applications. So in order to begin to compare different types of flow battery chemistries, I think it's important that we have an understanding of what parameters kind of dictate the performance of these. And this is what I've tried to summarize in this image. So if we look at these green boxes all around, these are the key performance parameters that are important to consider for flow batteries, but actually for any kind of energy storage device. So if we start here with energy density, this gives us an indication of the amount of energy that is stored per unit volume. If we look at power density, that's power per unit surface area, usually the electrode surface area. And what that essentially means is how fast you can charge or discharge your battery. So these are two important parameters, but if we're trying to design a storage device that's going to last, say, 20 to 25 years, there's also important considerations that are related to the capacity fade of that battery, the efficiency and cyclability, as well as its lifetime. And of course, economics are always a consideration for any energy storage device. And what I'm kind of trying to get across here is that all these, say, top level key performance parameters are related to some inherent electrolyte properties of those electrolytes in the tanks we talked about. So what do I mean by that? For example, if we look at the energy density here, so this is related, as we see, to the V cell, which I talked about previously, is related to the redox potential of those active species, as well as the solubility of those redox active species in the electrolyte. So those are the two electrolyte parameters that we want to boost in order to increase energy density. So in the same way, if we look at power density, we see, again, V cell as a consideration, and we also see that this discharge current that's actually related to the physical properties of the electrolyte, such as its viscosity and its conductivity and the kinetics of the redox reaction that's happening there. If we look at capacity fade, that's going to be given by the molecular stability of those redox active species. So again, we can see all these connections between top performance parameters and properties of the electrolyte. So now that we kind of understand what the flow battery is and what we need to consider, I'm going to give you a really brief summary of some of the typical types of electrolytes that have been looked at for flow batteries so far. And those have been can kind of be grouped in two different types. So the first one is metallic species, and the second one here is organic redox active species. So some of the typical metals that are looked at in flow batteries are shown again in this image here. And essentially, we're able to take advantage of the different redox states of these metals for electron exchange processes that take place in these batteries. And some of the typical ones that we've seen used are given here. So you might have heard of these because they're some of the most widely deployed. So they include vanadium, iron chromium, zinc bromine flow batteries. However, even though these have been kind of developed since the 70s and 80s, they have some inherent issues. So cost remains an ongoing challenge for, say, vanadium. Some of these other ones are less costly in terms of materials, but they have other issues related to the corrosion and toxicity of these chemical species. And an ongoing challenge is also the solubility of these metals. So if we think about this, what this means is essentially you can only really dissolve so much of, say, a metal-based salt in water or another electrolyte before it crashes out. And if we think back to the previous slide I have, that just sets a limit to the achievable energy densities. So those are kind of the challenges of metallic species, and these prompted research in the area of organic species. So these are all species that are formed with earth-abundant elements. So as we can see here, mostly carbon, oxygen, and hydrogen, and these species are capable of exchanging electrons. So they can be used in flow batteries and have been demonstrated. And the rationale there again was trying to move away from costly species towards something that's more sustainable. And these are the main classifications of them, but there's actually thousands of these molecules because they can be very easily tuned by introducing different functional groups. So that was the rationale for trying to research this area. But again, there's a new set of issues that kind of have appeared in this field related to them. So one of them is the crossover. So I described what that is previously, but essentially these small organic molecules can easily cross over from one compartment of a battery to the other. And in order to prevent that from happening, what's currently being used is very selective ion exchange membranes to kind of prevent that process from happening. So the issue with that is that those membranes are actually very costly. So even though we're using a low-cost molecule, that comes at the expense of using an expensive membrane. And the second issue with these organic molecules is their long-term stability. So many of these are actually organic radicals and therefore undergo a series of degradation mechanisms that kind of prevent them from being used for, say, thousands and thousands of cycles of a battery workshop. And both of these have been explored in aqueous electrolytes, so dissolved in water, as well as non-aqueous electrolytes, such as, say, acetonitrile and various carbonates. So I know that was a really brief summary, but what I really want to try to make you think about is the fact that there's currently several challenges that are in this area and that need to be addressed. So we've seen that solubility is an issue, and as well as this issue of cell voltages and solubility. So there's a trade-off there that I'm trying to get across in this image. So we see that we can tune the cell voltage to increase energy and power density. So non-aqueous electrolytes can achieve that. But at the same time, that comes at the expense usually of lower solubility in those systems. So that actually kind of sets the ceiling of energy density that we see here. So we're basically beginning to see that there's kind of trade-offs between all of these parameters. So I just talked about solubility and redox potential. I talked about previously organics being low-cost molecules, but also being molecularly unstable. We saw that we can increase the efficiency of the system by having this ion exchange membranes, but those are very costly. So there's all these kind of different trade-offs that we see in existing flow battery chemistry. So there's kind of an ongoing challenge to develop low-cost, highly stable new electrolyte chemistries that enable high energy and power density, as well as low species crossover. So that kind of motivates the title of my talk, which was Functionalized Electrolytes. And this is research that's being done as part of an EFRC that's called Breakthrough Electrolytes for Energy Storage that our group is a part of. And what the goal of this EFRC is to kind of break through in these performance parameters that we talked about by using new electrolyte chemistries where some aspect of structure can lead to a function. So this sounds a little bit maybe vague or difficult to understand right now, but hopefully in the next few slides you see what I mean with that connection. So the types of electrolytes that I will be talking about today are ionic liquids, redox active polymers, and again, NOMs that are the main materials I focus on. So let's start with ionic liquids next. So maybe you know ionic liquids from different areas of research. They're very widely investigated, but they're room temperature molten salts that are formed by a variety of anions and cations. And here in this image, these are some commonly employed ionic liquids for electrochemical applications. So ionic liquids have some desirable electrolyte properties that include their low vapor pressure, non-flammability, their broad electrochemical windows, and their high solvation strength. So they've been, again, researched in a series of applications, and this is kind of a nice review paper that covers them if you're interested. So how do these properties of ionic liquids give us some sort of function? So the high solvation strength of the ionic liquids translates into increased solubility of redox active molecules, which again translates into energy density. And I think this study here demonstrates this effectively. So this study used an ionic liquid to bind to 4-hydroxy-tempo, which is one of those redox active organic species. And they were actually able to boost the solubility of this tempo molecule to about double what it is in water. So that again translating to a higher energy density battery. And an additional advantage here is that by binding to the organic species, the ionic liquid was able to improve the molecular stability of this compound over many cycles. Again, a challenge that we talked about for the organics. So we kind of see that these ionic structures that bind species have a dual function of increasing their solubility and also improving the stability of these redox active molecules. So the next example I'm going to give is redox active polymer electrolytes. And what these are is high molecular weight compounds that have a redox active polymeric backbone. And that backbone can be several different things, can be organic species, can be metal-based species that are all in the polymer canopy. So they're able to exchange electrons that way. And the idea behind this is the principle of size exclusion. So what that means is that if we have a redox species with a larger hydrodynamic diameter, so larger size, we don't need such a selective membrane to prevent its crossover. So instead of using something like an ion exchange membrane, we can use a dialysis membrane or a size exclusion membrane. And the first study that actually reported the use of these redox active molecules, they're shown here. And we see these are based on organic species. And what we can see on the top left there is that this battery was actually able to maintain capacity over several cycles, even with the use of a size exclusion membrane. So those polymers were not crossing over, even though the membrane was less selective because of their large structure. So this is, I think, another example of how structures of electrolytes can be used to give some function in a battery. And this principle has been extended not only to polymers, but also to larger molecules, such as micelles or colloids that are shown here. So this brings me to my own specific area of research. And our question we were asking was whether we can design materials that can separate the redox active and conductive phase of an electrolyte, as well as target different redox active materials to increase their solubility. And in order to do this, we are using these materials called NOMs. So I'll finally explain what these are now. So NOMs are nanoparticle organic hybrid materials. They're essentially polymers tethered onto nanoparticles. And we've used a couple of different types of polymers for this. The main ones I've looked at are polyetheramine, which has the structure shown here. So we see it has this ether group functionality, as well as non-PI that is constituted by amines and is formed by polyethylene amine. So these are the main types of polymers, but these materials are highly tunable. So we can think about tethering different types of polymers to the nanoparticle. And these materials are beneficial because they're liquid-like and also have high thermal stability and negligible vapor pressure. So these desirable properties means that they've been explored in a series of applications. So they've been explored as electrolytes in lithium metal batteries. And this was primarily done by the Archer group at Cornell. And in our group, we've explored them as CO2 capture media. And this has constituted a lot of the work in our group so far. So if we begin to think of NOMs as electrolytes, this is a summary of kind of all the studies I've done trying to understand their function and their properties. So in the left here, I'm showing I've investigated the chelation of different redox active species by gnomes, and I've also looked at how we can tune the physical properties of gnomes by controlling their intermolecular interactions. So I'll go into more detail of this in the next few slides. So beginning with here on the left, the chelation properties of gnomes. So our first idea was whether we could have gnomes that can coordinate redox active species to improve their solubility. And we approached the study first with using gnome PI, which has those amine groups, and we looked at the coordination of gnome PI towards copper. And the reason we chose that was because, as we can see here on the left, it has a higher binding energy towards PI than other metal-based species. So if we have copper salt in solution, which is shown in this little picture here, and we add non-PI to it, we see this dark blue color, which is characteristic of a copper ammonium complex. So that gives us an indication that complexation was indeed happening. And we were able to study this doing UV visible spectroscopy here, which gave us an indication of the coordination number of the amines towards copper, which we found to be about 3 moles of amine per mole of copper. So now that we understood how non-PI was chelating copper, we did an electrochemical study, and this was in collaboration with a group at University of Tennessee. And these below are kind of our findings. So the first image here, this is just the electrochemistry of copper in the absence of gnomes, and we see 2 reversible reduction and oxidation peaks here. And this is the effect that the addition of gnomes has. So there's kind of 2 things to point out that we found out. So the first one in the second image is that we begin to see this appearance of a secondary electrochemical peak, which suggests that the coordination of gnomes is stabilizing the copper 1+ oxidation state rather than the 2+. So there's kind of an intermediate in that reaction versus what would just be happening in a normal aqueous electrolyte. And the second thing we found was that as we continue to add gnomes to the solution, so as we go down here, this is increasing the concentration of non-PI in solution, we see this kind of disappearance of the electrochemical peaks beyond that saturation concentration. So this indicates that the binding energy of non-PI to copper is so strong that we actually begin to see electrochemical peaks disappearing. So this was an interesting finding, but our goal is how we can chelate redox active molecules, but also have reversible electrochemistry. So we began to think about how we can tune that chelation to actually be able to harness those redox active molecules, right? So what we did is on the next slide, we studied the effect of pH in solution. And if you look at the top UV visible spectra here, you can see that this peak that gives the characteristics of those complexes is actually decreasing in intensity as we lower the solution pH. So we began to think that the copper ions, and the protons are competing for those amine sites that we see along the polymer chains. And we began to think of chelation being tuned by the pH, and we can think of things like a pH swing to kind of catch and release redox active species on electrode surfaces. And if we look at the electrochemical study, we see exactly the same thing. So this is 3 different studies with different ratios between the amines in the chains and copper. And we see that all the ratios, as we lower the pH, we see this appearance of the electrochemical signals. So again, suggesting that the chelation of these copper ions by the molecule can be tuned via the pH. So now I'm going to change gears a little bit and talk about the physical properties of gnomes. And we spend quite a lot of time thinking about this, and the reason is that gnomes are challenged by their very high viscosity. So I think this is clear if you look at the image here on the left. So this is the viscosity of gnome HPE in water, and we see that past about 38% gnome in water, we're already above 100 centipoid, which is very high viscosity that challenges the actual use of these electrolytes in an electrochemical application. So we've been thinking of ways to tune this viscosity. And one recent study that I've been doing is looking at the effect of ionicity. So in this plot on the right, sorry, I'm showing 10, 30, and 50 40% NOM-HP in solution. And the dashed lines here represent the addition of salts to those solutions. So zero 0.1 molar sodium chloride. And we begin to see very significant decreases in the viscosity of these mixtures. If we note that this is log scale, so that's about an 80% reduction in the viscosity of the NOM-based mixture. So this was an interesting finding, but of course we were curious to know what's actually happening here on the scale of a single NOMS molecule. And we used dynamic light scattering, or DLS, to kind of probe this effect. So this that you see here on the top right, this is the distribution of the size of NOMS molecules in solution that we obtained from DLS. And we see that in the absence of salt, so that's the blue curve we see here, the size of NOMS particles is about 35 nanometers. However, when we add the 0.1 molar sodium chloride, we see that this size is actually decreased to about 18 nanometers. So we began to think that actually the polymer canopy of NOMS is responsive to these changes in ionicity. So in a water-based system with no added salt, those polymers are actually able to swell, which leads to this increased size of NOMS. However, when we add those ionic species, those are interacting with the polymer canopy, and that leads to those polymers actually kind of collapsing, and we see this decrease in size. And we kind of, to probe this further, we did a viscosity study where we continued to add salt and kind of investigate at what point the viscosity will no longer decrease. And again, we see that there's kind of a critical concentration where viscosity remains constant. So based on this, our current hypothesis is shown here. So we see from these studies that it seems the polymer chains are interacting with these ions, which leads to their configuration to change and them to collapse. And we therefore see this decrease in the viscosity. And eventually, if we continue to add salt ions because these polymers are saturated, this viscosity will no longer change and remain constant. So in the same way that we can tune intermolecular interactions by changing ionicity of the mixture, we can also begin to think of using different secondary fluids. So that just means dissolving NOMS in something other than water. So this is a study that I've been doing with Tony Ferrick, who is another student in the work group here. And what we found is that we can choose an secondary fluid that has different interactions with the polymer canopy. So let's look at this image on the left here. So this is, again, viscosity over NOMS mixtures. And if we look at the plot with water, we see quite high viscosities because water is able to hydrogen bond with the groups in our polymer chains. However, if we look at another secondary fluid that has a lower polarity, such as toluene, we're able to see that we can actually reduce the viscosity of those mixtures significantly. And again, DLS was kind of useful to understand this process and related to the changes in the canopy. So we see the size of those polymer chains is actually changing based on the chemistry of the secondary fluid. So to summarize in terms of what we know about NOMS-based electrolytes, we've seen that the structure and the properties can be related to the chemical environment of NOMS. So we've seen chelation properties are related to pH, and we've seen that physical properties are related to the canopy configurations, and those are responsive to changes in ionicity, as well as the choice of secondary fluid. So based on this, I have a couple of new ideas and directions that I'm going to try to explore in the future. So the first one is other potential swings to kind of catch and release molecules near electrode surfaces. So we've seen pH swing is a suitable option, but I'm also trying to think about whether maybe a change in temperature or ionicity swing could lead to the same effect. And I'm also trying to design NOMS with different types of polymers where we can tune the binding energy between the functional groups and the redox active molecules to be able to coordinate these molecules, but at the same time have reversible electrochemistry. And finally, I'm also looking to synthesize NOMS that have a redox active polymer backbone. So rather than actually binding to a redox active species, I'm thinking of going towards NOMS that are redox active themselves. So that's a similar idea to this redox active polymers I talked about. And finally, I'm thinking of trying to functionalize the core of gnomes. So for example, going towards magnetic nanoparticles as cores, where we can potentially control the flow of gnomes using a magnetic field. So it's just a brief overview of what things I'm thinking about, and if you have any ideas, I'd love to hear them. So as we continue to research this area, a series of questions have emerged. And these are basically related to how the structure of these molecules impacts electrochemistry. So we're looking to investigate how structure impacts electrochemical response, how electron transfer actually takes place in these molecules, and how structure changes near electrode surfaces. And here I'm showing two studies that looked at ionic liquids and polymers to try to answer these questions. But in terms of gnomes, these questions are very much open, and that's why I'm still doing very fundamental research to kind of try to probe these different effects. So this is my last slide, and these are kind of some takeaways and summary. So I hope you learned something from my talk, but if you have to take something away, hopefully you understand that electrochemical energy storage involves all sorts of trade-offs. And if you've taken any battery course, etc., I think this is what I got from many of the battery courses I took in the department. And hopefully you've also kind of begin to understand how new electrolyte chemistries open up these possibilities of how their structure can facilitate a function in a larger battery application. And again, I just want to emphasize that there's definitely a lot of new questions to explore and unravel that I'm still trying to understand as I probe the role of these electrolytes further. So with that, I'd like to thank everyone in my research group and all the students I've worked with in the past, as well as my collaborators and funding agencies. And I'm really looking forward to the discussion and hope you guys have many questions. So thank you, everyone.
You have a few questions in the box. Thank you so much, Sara.
Yeah, no problem.
Would you like us to read them to you, or do you want to go through them?
I think I managed to open the box. Let's see.
Okay.
Are any polymers in commercial use? Okay, so the redox active polymer based flow batteries, I'll go back to that slide. So these flow batteries, they were only really like the first paper that came out on these was in 2015. As far as I know, they haven't been demonstrated on a commercial scale, but the polymers they actually use, many of them can be bought online on like a lab scale, but there's also work trying to synthesize and tune those polymers that is done in organic chemistry labs. So these batteries, as far as I know, are not commercialized. Okay, next question.
Sara, can I ask a question, follow up?
Yeah, of course. Yeah, please.
So, you mentioned towards the end, actually, some redox active polymers themselves. There was a lot of work done in the 1990s and even before, sulfur-based redox active polymers. Have they been looked at recently at all, or?
Yeah. So this field here was kind of building up on the knowledge that was developed in, I think it was the 70s or 80s. I think polyvinyl ferrocene was kind of the first polymer that began to be studied, but those studies were mainly focused on understanding the electrochemistry of those polymers, at least as far as I understand. This was the first study that actually demonstrated the size exclusion principle by doing a flow battery test. But there's definitely a body of knowledge of what the electrochemistry of those polymers is.
But nothing commercially used?
I think so. I can add to it. So I think there's EFRC doing really fundamental research in this area because there are challenges. Mm-hmm. And according to them, they do definitely prevent from crossover, which is solving one problem, mm-hmm. but their redox activity goes down. Mm-hmm. So it absorbs onto the surface of electro a certain way, and it doesn't dissolve or it's not as active. And how to connect to the multiple active sites, those mm-hmm. became a little more complicated. So I think we are still in the fundamental research level, okay. Not commercialized yet.
Okay.
Um, did you have another question? Do you want to address all your questions now?
I had another one. I think you're using the initial experiments, I think, potassium nitrate as there. And then I asked the question, what happens if you have a chloride ion that would stabilize the cuprous CO1 plus? And then you showed some effect of sodium chloride, but for a different purpose, you were using sodium chloride. And I was just curious, what happens if, when you run the cyclic voltammetry, what happens when you have a chloride ion sitting there and it stabilizes the CU1?
Yeah, no, that's a good question. And I'm actually trying to go towards investigating both nitrates and chlorides as supporting electrolytes in the future. And my intuition is that that would affect the coordination of
Yes, you will.
Yeah, that's definitely something I'm planning to explore, but I don't have an answer for you. Yeah.
Okay. And I think there was the last question I asked. What did I have?
The passivation over time.
Oh, yeah.
Yeah, I'm reading it.
Yeah,
that's a big problem, right?
The passivation over time of the
electrode surface, whatever electrode surface you use.
Yeah, so my understanding is that in conventional batteries, passivation isn't really an issue. And I think as we begin to explore these new electrolytes, again, understanding the interface between the electrolyte and the electrode is still an area of fundamental study. So if I go back to the slide with the final questions, this question was actually addressed for polymers in a very recent study. So this work tried to investigate this passivating polymer film that's forming on electrode surfaces.
Okay.
So there's definitely a potential interaction between a charged polymer and electrode surface. And I think we're very much still trying to understand that in the case of gnomes.
Excellent. Very nice talk, by the way. Congratulations.
Thank you. Okay, I'll try to move into the next talk in order. Okay, so I think Ray had a question related to the interfaces in the systems. Ray, do you want to verbalize this or?
Yeah, there's certainly a couple of interfaces. I mean, the obvious one is membranes, and if you see any fouling. But the other interface, which I think is important for you with the gnomes anyway, is the polymers that are attached to the silica particle. Mm-hmm. As you cycle back and forth to either expand or contract that layer, those are metastable states, right? So you don't get the same thing every time that you expand and contract, and accessibility to the binding sites might be different.
Yeah.
And so I'm just wondering if you see any effects like that, but more fundamental, and I think one of the subsequent people have asked this online, is if you're connecting your electroactive species to a large silica balloon, doesn't that slow things down? Or unless there's a hopping mechanism that occurs, I don't know.
Yes, 100%. I think those are all definitely important considerations. So in terms of a point you mentioned, material utilization, so it's very possible when you begin to have these large redox active structures, you can't actually, my understanding is that you can't always access all of the charge along that canopy. So the research that has been done in redox active polymers has kind of found that as a limitation. So that's definitely something to consider. And in terms of your second point related to the diffusion of these molecules, again, that's a really good point. So if we look at these redox active species, this sounds like a very promising concept to kind of couple these with these non-selective membranes. But again, if we think back to the hexagon, again, there's a trade-off. So we have molecular stability and we have reduced crossover, but the diffusion of those molecules is definitely lower than those of single ions.
Well, classical diffusion, but if you can engineer a hopping mechanism, right? There's something called a Grothus mechanism for protons anyway in ionomers, for example. And essentially the proton just hops from site to site while the sites more or less don't move very much. They wiggle a little bit. I don't know if it's possible to do that with, let's say, copper ions or something like that.
So actually, the other student, Tony, is working on it similarly. So what happens is we cannot use gnomes as a pure form. Lyndon Archer at Cornell uses the almost pure form. So
Yeah.
his material is almost like a gel-like, so almost like a solid electrolyte.
Yeah.
But our material is very lower viscosity fluid by adding secondary fluid. And what we found out earlier, a few years ago, was if you have a mixture of nanoparticle with the polymers with the water versus gnomes with water, we totally thought that the viscosity will be higher with the gnomes because there's a whole bunch of nanoparticle. Plus that lower the conductivity because, again, there's a lot of the nanoparticles. That's what we expected. And what we saw was exactly opposite to what we thought, that for that particular case. So we were getting confused. Of course, it's really depending on what is the secondary fluid and what is the mixture. But in that mixture was that way. So I was getting all confused. And we went back to synchrotron to understand the structure. And what we saw was that there is a multi-scale ordering of these gnomes within the secondary fluid, depending on how much hydrogen bonding we have. So then we can tune that structure. So if you look at just if everything is evenly distributed, there shouldn't be overlapping of polymer to polymer because they're far away from each other. We put gnomes quite low concentration in terms of volume. But then when we looked at actual interaction, we see it in NMR and all these data that they do have interaction, which means that there is a clustering in a unique way, and that somehow enhanced the transport behavior. So hopping, I think we do think it's happening, but it's really depending on competition between hopping with the binding energy and all that so on. That's what Tony and Sara is looking at, and what Sara talked about in one of her slides was by adding salt, which is competing with not only proton or cation redox active species. There's a lot of competition for the binding site, and depending on that, things going in and out of these functional groups are very different. Very interesting phenomenon.
As long as you don't add too much salt and coagulate the nanoparticles. You might want to think about, I don't want to dominate the questions here, but you might want to think about using dynamic rheometry to look for interactions amongst your particles, in addition to just measuring viscosity. But thank you very much. Very well done.
Oh, thank you. I'm going to take note of this new technique.
And I think there's a question from Dan Steingart, Professor Steingart. What functionality can gnomes, Dan, could you ask?
Is Dan here?
Yeah, he is here. Dan?
I'm sorry, just unmuting. Yeah, so really nice physical chemistry, Sara. But as we spoke about sort of many times before, I don't get it. So I don't get the I don't get the performance hypothesis, and I'm trying to understand it. So the idea that one can stop crossover, I appreciate, but it looks like beyond the diffusion and IR losses that one gets because of the large tether, with the hopping mechanisms that were discussed comes, you can add a salt, the salt can be a supporting electrolyte, but then you decrease the, you decrease limiting current significantly, which is, as I understand it, crucial for the scaling, the economic scaling of the flow batteries. So I guess my question is this, and it's loaded because it's something that I tried to get across in the courses that I taught. At what point can you look at an approach and say this is not effective, instead of trying to thread the needle and say this is effective? We've been doing this for a little bit now. And so, are gnomes going to improve a system in a given way, or is a class of solutions that's interesting for electrodeposition and interesting for process engineering solution modification, but just too constraining for energy storage? I know that's a very loaded question, but you're halfway to graduation now, so I get to ask you these types of questions.
Yeah, thank you. That's a good point. And yeah, I was expecting a question from you. I think first off the bat, I'll say that these studies are still very fundamental. So I don't think at this point it's feasible to say that, you know, using gnomes in a flow battery is going to lead to this specific breakthrough. And I think we're still trying to understand their physical properties and how we can tune those to lead to some sort of specific function. So my understanding is that the first goal here is to design these materials to boost the solubility of a redox active species. So as we saw, these gnomes are very effective in coordinating different redox active species of interest. So I think that's kind of the first function. But as you said, 100%, there's all these new challenges that are appearing. And I just talked about viscosity, but again, multiple challenges related to how these particles diffuse. And I think that's still very much a question that we're trying to understand, is how we can tune these properties that gnomes have to lead to some sort of improvement. But again, this is very fundamental research. And
yep. No, I appreciate it. So let me ask a specific question here then. So with a given gnome, how easy or hard is it to tailor the number of ligands or chelation points that are hanging on the nanoparticle? Is there a specific number that you expect, or is there some statistical distribution of I'm going to say little hairy points that are hanging off the SiO2?
It's quite easy to tune that, because when we synthesize the gnomes, we can change the amount of polymer we tether onto these by changing the graphene density. And of course, there's kind of a limit given by the surface area of the particle. So in terms of increasing, there's a limit, but there's we can definitely go less the nanoparticle. And then in terms of the number of chelating sites of the molecule of the canopy of the polymer, we can increase the number of chelation sites by increasing the molecular weight of the polymer. But then that will lead to inherent challenges related to even higher viscosity over systems and less flowability, etc. So
got it. So then at what point, right? Because I think you have enough. So based on that, you've got enough information now to make an estimate on potential energy density improvement or decline.
Yeah. So with the current, I did kind of like a mental experiment, I guess. With the current that I showed of the copper being tethered onto the amines, if we use 100% gnomes in solution, which is, you know, unrealistic for other purposes, the effective molarity of that mixture is about 8 molar copper.
Okay.
But again, with all these limitations, we can't really have 100% gnomes as an electrolyte because it's not.
Sure, but what's interesting is that I was intrigued by your recent paper. Congratulations on that, or at least I look forward to reading it if it's not published yet. I saw that it was just accepted. That at a certain point, the copper never comes off.
Yeah.
So you've succeeded in increasing the quote unquote solubility, but I'm not actually able to use all of it, right? And that's kind of fascinating. And so can you talk a little bit more about that? Because now you've introduced maybe, you know, a new Hamilton parameter that's not quite solubility, but accessibility within a flow battery.
Yeah, 100%. That's an important consideration. So again, we saw these gnomes were effective in chelating copper, but that copper that's chelated, from what we understand from our results, is not actually accessible electrochemistry. So that's why we began to think of ways in which we can release those redox active species. So ideally, we'd be able to have high concentration of a species in the electrolyte, but then near electrode surfaces release that. So that's why we studied pH as a potential swing. But again, I understand that's not a very practical thing to do.
But it's just sort of interesting, right? Because like, I don't know, and I refer this back to our mining cleanup experts, Dr. Farinato and Nagaraj, because like it seems to me that if you have something that can soak up 8 molar of copper and not give it up, like this is a wonderful tool for cleaning up mine drainage sites, right? It's like a sponge.
My concern also.
As long as you can release it eventually, yeah.
No, the thing
Otherwise,
is,
it's expensive sponge otherwise.
That's right. That's right.
You can't just count the number of tethered molecules, right? Because you have each molecule has tertiary nitrogen, secondary nitrogen, and a primary nitrogen, if you are using PEI, that is. And you got several complexing sites, not chelating sites, complexing sites. So you have, for each complexing site, you have a stability constant driving this whole exchange of copper versus proton. So it's far more complicated than just counting the number of tethers. So that's why I was also, Professor Steingart, thanks that he asked the question. I have a million other questions, but anyway, it's very fascinating stuff going on there.
Yeah, thank you for those thoughts. So just to finish replying.
Oh, I don't want to hog this.
So just I thought for you that's definitely a good point, and we're actually thinking of beginning to use gnomes to extract different elements such as rare earth elements for some of our other projects related to waste. So I think that's definitely something to consider. And then to finish answering Dan's question, so yeah, I'm currently trying to look at ways in which we can selectively release these redox active species from gnomes. And at the same time, I'm trying to look at gnomes with more reversibility. So currently I'm looking at the ether-based gnome based in zinc, which is has a lower binding energy. And the hope there is that we'll see higher reversibility as
I mean, in general, the chelate is stronger than, right? When you have one copper that's bound to 3 nitrogens or 2 nitrogens is much harder to strip than a monodentate complex. And so lability of a complex is probably what you want to consider. Put it on your, what's it, hexagon or pentagon, showing solubility and all that. Put lability of the complexes.
Yeah.
And that is probably what you can measure very easily and predict also.
Yeah, no, I think those are great thoughts. I might send you a follow-up email if that's okay.
Okay, very good.
And we, in our group, because we do mineral carbonation, we also looked at always ligands or complexing agents we use has to be strong enough, but not too strong.
Yeah, right.
That optimization,
exactly.
because we're not going to just do it one direction. We have to be reversible all the time. But
That's
one
why
thing,
I think the
Sarah,
mobility is a good measure of that.
Yeah. So Sarah and my team have been discussing tuning that binding energy is important, but at the same time, why should we always grab onto cation? Maybe we can grab onto anion, right? And let cation to be more mobile. So there are many different versions of it we are looking at. So very complex, but interesting materials for sure.
Yes, it is. Yeah.
Thank
you.
I lost the chat box. Sorry.
I think Adam has a question. Adam, do you want to ask a question?
Oh, yeah, sure. So I'm completely ignorant to chemistry, as everybody knows. But this lab work absolutely fascinates me. And I'm curious, like, when you're coming up with these ideas and approaches, for example, like adding salt to decrease viscosity, where does the idea come from? Like, is it like math theory, or is it like some intuition you need to develop over years of working with these chemicals? So yeah, kind of a general question about like how the design process works, I guess.
Yeah.
Very cool talk, by the way. I really learned a lot.
Thank you. I'm happy to hear. Yeah, that's a really great question. So I think part of that comes from kind of understanding the way that different polymers interact with their environment, and that's something that I've honestly learned from taking classes and reading papers, and that's how I built my intuition, but definitely something that I'm continuing to learn. And just thinking of these different pH swings, temperature swings, etc., has come from that kind of knowledge that I've gained from just taking classes at Columbia, which is great. And in terms of that specific salt example, I was actually measuring viscosity because we added salt as our supporting electrolyte to increase the conductivity of the solution, and just kind of realized how significant that increase was, and then continued to do a whole study on it. But I wouldn't say it was 100% by chance, but I didn't plan that study per se, and just kind of continued to probe as I saw what the effect was, and I was trying to understand, what the physical chemistry was behind. So I think a combination of reading, taking courses, understanding the theory, and sometimes, just lucky days in the lab, I guess.
That's the story of my life. Thanks. That's awesome.
I think there was a question by Han Qing, but I think it was answered with the lump sum with other questions. Is there any other questions?
I don't have any other questions. Yeah, so actually it has already been addressed. Yeah.
Okay, thanks, Han.
Anybody else? Great. Well, thanks for the great talk, Sarah.
Thank you, Sarah.
Yeah, thank you very much.
Good questions.
Good luck to you.
And yeah, please send me an email if you have any ideas or other questions. I love to chat, so that'd be great. But yeah, bye everyone. Have a good weekend.
Okay.
Thank you,
Be
Sarah.
safe.
Bye.
Be safe.